The good busy signal of call admission control. Now you might wonder, when on earth can a busy signal be good? Well, when the call might be devastated if it were to allow to go across. Now, call admission control, in my opinion, is a form of quality of service. However, you won't really find it in any quality of service book because it's almost too specific a technology to voice over IP. Quality of service is designed to be a network strategy overall, whereas call admission control, as the name applies, just adheres to the voice over IP calls that are happening on your network. So what we're going to do in this video is talk about some pretty sweet technology. We'll first define what call admission control is all about, and then we'll get into the various types of call admission control, because there's all sorts of flavors of this that you can deploy. Some of them will be local mechanisms, and these are some of the simplest mechanisms you can use. We'll get into some pretty neat stuff of measurement-based call admission control mechanisms, which really starts implementing something known as a probe. It's pretty awesome because you can send these little capsules around your network that test the quality of all your lines and come back and report on that quality, saying, hey, this is a great WAN connection, or maybe this one's a little shaky, you might want to divert. That's what the measurement-based call admission control gets into. Then we'll look at resource-based call admission control, which ensures our WAN bandwidth is at the level it's supposed to be at. Before we get into the nitty-gritty configuration, let's first define what call admission control is all about. Call admission control, and it's commonly abbreviated CAC mechanism, CAC, allows you to protect the WAN from running out of bandwidth. Because it's a common misconception, I thought this when I first got into voice over IP, that if you start sending calls across the WAN and it runs out of bandwidth, well then just the future calls will have pretty bad quality. Say the WAN has enough bandwidth to support, we'll say 5 voice over IP calls. Well, as soon as the 6th one comes across, the WAN is then out of bandwidth. And you're going to start dropping packets, not just from the 6th voice over IP call, but from all voice over IP calls. So all the quality for all your calls begins to plummet very quickly. So one of the key features of call admission control is to protect that WAN from running out of bandwidth. It protects voice calls from other voice calls. Now, quality of service, let's make sure we draw the line in the sand here. Quality of service protects the WAN from data applications, or lower priority applications, I should say, from overwhelming your voice over IP conversations, because data applications can be bandwidth hungry, so they can easily crowd out voice conversations. Quality of service solves that issue. That says, okay, we'll reserve this amount of bandwidth or prioritize voice calls up to this amount of bandwidth so the data applications can't touch them. But that doesn't protect when you have too many voice applications overwhelming the WAN. Quality of service just says, voice, you get the priority. But if you have too much priority traffic, well, at that point, the priority traffic begins beating each other up. That's where call admission control comes in. It allows you, when the WAN runs out of bandwidth, or reaches its bandwidth limit. Runs out of bandwidth sounds pretty devastating. Just reaches a predefined limit that you've set, you can deny future calls from going across the WAN and forward them off to an alternate path, the PSTN. Or maybe just give a busy signal for future wide area network calls if you don't have some sort of secondary path in the picture. When you hear a definition of call admission control like that, it sounds like one tool. It's kind of like, oh, if the WAN's out of bandwidth, switch over here. But there's many different tools that you can use within the call admission control category that give you a ton of different options when you're setting this up. The first one that we have is the simplest, and we'll go through each one of these categories and tell all the individual tools in each one. The first category of tools is local call admission control mechanism. Just like this little magnifying girl here, she's inspecting an individual device. It means your router is going to be inspected individually. It's going to look at all its local resources, as in, how many calls have gone out on that dial peer? Or how many channels do I have on that T1? And if those are exceeded, then it says, well, I'm out of bandwidth, I'm out of channels, let's switch over to the next dial peer. It's a very simple mechanism, but also it's really effective. So those give you a lot of flexibility there. Now, in my opinion, this one is by far the coolest category of call admission control. It's like this little probe action, the little Star Wars droids. They send these droids out to kind of inspect things, Have you guys seen Star Wars? You have to see Star Wars. If you're watching Star Wars, they have these droids, and everybody's hiding from them, because it's always like, oh, the droid's coming, duck, and everybody gets down, or some lightsaber comes and chops the droid up, and so on. In the world of Cisco, you have little droids that can be sent out on your wide area network connections. Now, these droids are engineered, masqueraded, as different types of traffic that you can send. See, this works not only for voice over IP, but for any category of traffic that you want. Here's the concept. I could send a probe out on my wide area network link that looks like web traffic, and it will fly over to the other side, and the router on the other side gets it and goes, you're a droid, I'll send you back. Back it goes and is received, and it records all the statistics of what happened to it. It may come back, missing a leg. It's like, oh, I got beat up. My delay was intense. I got overwhelmed. I nearly got dropped. It's sending all this report about web traffic. Now, we can also engineer these droids to look like voice over IP. So we could send out a little voice droid or a bunch of little voice droids, and they're like, going across, and we can see how they're treated. Now, the reason that I'm making such an emphasis on these droids can emulate different types of traffic is just as you saw in the previous videos. You can set up quality of service to treat traffic differently. We may have one mechanism that treats web traffic fairly poor, whereas another mechanism treats voice traffic very well. And a lot of people think, oh yeah, I can just test the link by sending a ping, and watching the delay of the ping message. Well, first off, ping messages are very small. And second off, they are of the type ICMP. So, ICMP may be treated one way, but voice or HTTP or all these other traffic classes might be treated totally different. We can engineer these droids to look exactly like web traffic, or exactly like voice traffic, same packet sizes, same packet shapes, same port numbers, everything, and see how those droids are treated. And then, once we see how those droids are treated, we can make a decision of whether or not we would like to use that connection. You might have a variety of WAN links, or maybe a PSTN backup. And you can say, whoa, voice droid just came back. It's pretty beat up. Let's switch over to the PSTN for all future calls so that we can ensure our voice quality meets a certain level. Now, in the meanwhile, we'll keep sending those little droids out. They'll be happily going across the WAN and sending their reports. And as soon as we get the quality within a certain level, those droids come back unscathed, we can say, okay, WAN link's good, switch back over, let's use that for our voice over IP calls again. See, I told you this was cool. Measurement-based call admission control is indeed the most flexible, I think, way of configuring call admission control. The final way is called resource-based mechanisms. And in this category, we really have gatekeepers, which I've mentioned a little bit earlier when we talked about the H323 protocol. Gatekeepers watch over the wide area network to ensure your resources don't run out. In this case, our glass is half full, and as things begin to take those resources, that bandwidth, we're going to start seeing it go, oh, new level, it's going down, drinking water, and once we get to the bottom, we can say, oh, resources are gone, let's go ahead and divert. Also in this category comes a mechanism called RSVP, which allows you to reserve bandwidth for the call. And I'll show you that configuration when we cover these mechanisms one at a time. Let's start by taking a look at the simplest call admission control mechanisms, the local ones. The first call admission control mechanism requires no configuration because it's on by default and it just makes sense. It's the physical DS0 limit, meaning if we had a T1 line, as a matter of fact, let me bring up a router here. I'm going to type in a show voice port summary. Hit enter. You can see that I have a T1 line in this router, and I only have 2 of the channels of that T1 configured. This is a CAS connection that's using FXO loop start signaling. You can see that I have the T1 installed in port 0/1/0. You have the :0 because that's the DS0 group that's configured. I have channel 1 and channel 2. Now, each one of those channels is a physical DS0, which means if you have a connection and both of your physical DS0s are used up on your channels, or however many physical DS0s you have, the call won't go through. It will say, okay, I'm out of channels. Either look for another dial peer with maybe a higher preference, or just go ahead and busy the call out. That just makes sense, and that's turned on every Cisco router by default to zero out the call if it runs out of DS0s on a T1. Now, the maximum connection limit is more on your side of the ball game. You need to configure this one. Now, I have two routers connected here, and I didn't label the connections because they could be anything. This could be two, WAN links. It could be two frame relay links. One could be a WAN link. One could be a PSTN connection. It could be absolutely anything. And let's say that just for the sake of argument right now, and it's because it's what I've already configured, we have two voice over IP dial peers set up. I have them on this router pointed towards this router that has a PBX behind it with 4 3 ... extensions. Take a look. I have on my router, I'm going to do a show voice, or actually dial peer voice summary. And right here, I have dial peer 43 and 44, both of them being voice over IP dial peers. You can see that I have them pointed to two different IP addresses. So, in this case, two different WAN links. You can ignore that they're from the same subnet. Well, actually, they could be a 30-bit mask, right? Just an example. We have the same destination pattern configured on both of those, one with a preference of 0, one with a preference of 1. Now, with what we know about the preference command, the 0 will be used right now unless it's down, meaning it can no longer reach this IP address on the other side of the connection, at which point it's going to fail over to the dial peer that has a preference of 1. Now, this is where the maximum connection limit can come in. Let's say that I know, because I've done my homework and I've set it up with quality of service, that this top link, the one that uses the destination IP address 192.168.100.5, we'll say it's this one right here, across the top, can only handle a maximum of 10 calls. Now, what codec that is up to you. It doesn't matter because the router can track the active calls. Remember that command, show call active voice, and I could put a summary on there, and it shows, how many active calls there are going across that link at any one time. Well, check this out. I can get into global config mode, go under that dial peer. Let's go ahead and access dial peer voice 43. And I can type in the command max-con. That's the full command, not max connections, max-con. And the maximum number of connections that this dial peer can handle. Now, by looking at that maximum number, I think we don't even need to do the negate sets to unlimited, because if we type in 214 million something, or 2 billion, I think that is that number, I don't think we'll be exceeding that unless we're an intense service provider. But we could type in no maximum connections if we want to negate this. But I can type in maximum connections 5, enter. Or did I say 10? I think I said 10. 10. And at this point, as soon as this dial peer detects 10 maximum connections going across, it will zero out that dial peer, meaning future voice calls that have 43 ... 43 and any two numbers as their destination will not use that dial peer until the maximum connections drops below whatever I've set to be my maximum number. Future calls will fail over to this dial peer, which may have its own maximum connection limit on there. So that's really cool, because with what we know about quality of service, I can set up my priority bandwidth to zero out, meaning once it reaches, we'll say 500 kilobits per second of priority bandwidth, that connection limit is reached, which maybe is 10 calls or 5 calls, whatever the codec I'm using will chomp up the certain amount of bandwidth. At that point, it fails over to the second wider network line. The last type of local CAC mechanisms that Cisco has implemented is one called Local Voice Busy Out, or LVBO. This is where you have a router, and this I've drawn out a diagram where this is most useful. You have a router connected to the PBX, but maybe you're in the midst of a migration, meaning instead of moving all the PSTN and everything over to the router, maybe you have it to where the PBX is still connected to the PSTN, and you've just implemented a router to do toll bypass between your two locations. So you haven't actually moved the PSTN connection to the router yet. This is actually a real common type of configuration. I mean, why would you want to move the PSTN connection to the router and purchase an interface and everything like that when you already have the PSTN interface plugged into the PBX? And I mean, you don't really need to run the PBX through the router. Maybe you also have limited ports available that's connected on the T1 line to the PBX as well. You don't want to have to run everything through the router. So you might have a configuration like this. Well, if this serial link were to fail, let's say it just goes down, or maybe, experiences some kind of communication failure, it's kind of going up and down, it's flapping, you can configure local voice busy out, which will busy out your T1 line to the PBX, meaning the PBX will detect that this line is busy and use its own failover mechanisms. PBXs can do this too, to fail over to the PSTN and go across to this PBX, rather than using the toll bypass tie line up here. I just combined two different terms there. Toll bypass to avoid the tie line. Instead of using the toll bypass, you can have it go straight across the PSTN. Let me show you the configuration, and this will make a lot of sense. I'll bring up this router, and let's go ahead and do a show voice port summary. Oh, I have a dash in there. And I have my two FXO ports configured right here. Maybe those are the ones that are connected directly to this router on this T1 connection. FXO is a valid trunk type to come over to the PBX. So what I can do is I can jump under the voice port. I'll get into global configuration mode, and I'll type in voice-port followed by 0/1/0:0. We're now accessing that DS0 group that has those two channels going to the PBX. I can then type in the command busy out monitor and then the interface that I want to configure. Oh, am I typing that wrong? Busy out my, oh, here we go. We don't even need the interface command. I'll type in serial, and the serial port, what is it? I forgot what it is on this router. Let me just do a show IP interface brief. The serial port is serial 0/3/0. So I'll type in busy out monitor serial 0/3/0. And I hit enter. At that point, what happens, and in this case it's happening right now, as soon as it detects that that serial interface is down, it automatically busies out those voice ports. So those will no longer be active. If somebody picks those up, meaning the PBX tries to use those, it will give a busy signal, causing the PBX to use whatever failover mechanism it has, and maybe it just plays a busy signal. It doesn't have any failover. But if it does, it can transform that call and send it out to the PSTN across maybe a tie line or just the standard PSTN connection to reach the other side, instead of forcing the call to go across the wide area network connection. Now we get into the cool call admission control mechanisms, like the measurement-based systems. These are the ones that use the probes. Yes, the cool ones that emulate voice traffic across the wide area network, and then based on how that traffic is treated, makes a decision of whether or not to use that path. I mean, even these names sound cool. Advanced Voice Busy Out, or AVBO. It sounds like Taibo, where you learn kickboxing. Well, just like its predecessor that we just saw, LiveBo, the local voice busy out, this is kind of the new and improved version. Not only will it check and see if that wide area network is down and then busy out these ports to the PBX if so, but it will also send those probes across that line and test the connection to make sure it's okay. And if it falls below a certain quality level, then it will choose to busy out those lines anyway. So, here's how it's configured. AVBO. You jump on your router, not literally, and you get under the interface, the voice port interface, that is going to use that connection. So in this case, let me get familiar with this router again. Show voice port summary. I hit enter, and I see I have those two FXO ports that are I have trunked over to the PBX. Now at this point, all I need to do is get under those voice ports, and I'll type in voice-port 0/1/0:0 and type in a single command. That busy out monitor looks the same as LiveBo, right? But instead of saying an interface like that serial or loopback or whatever interface I'm looking at, I'm saying probe. I type in probe followed by the IP address of where I want to send that probe to. Now let's look back at the diagram. Let's say that this IP address, we don't have it there, but let's say it's 10.1.1.1. 10.1.1.1. I hit a question mark. Now it's coming up and saying, what kind of codec do you want to emulate in that probe? What kind of delay time, the grace period before reporting an ICPF IF failure? And then what is the I can't even say ICP-IF threshold. Now, this ICP-IF is a form of electronic measurement. Remember, we saw in the quality of service nuggets, we saw the human MOS score, the mean opinion score, where you had two people talking, and then we saw the system that could electronically measure the line. Well, this is an implementation of that electronic system. It stands for the ITU, Calculated Planning Impairment Factor. Now, what this is a system that rates the call based on delay, based on packet loss, on a scale of 1 to 50, or 0, I guess you should say, 0 to 55. And really, 0, oh, I've got my wrong tool here. 0 is a flawless call. If you had a call of 0, that means, perfect, excellent, no impairment at all. So, I mean, that you really don't even count that category. 5 means the call is very good. I'll just put a little VG there. Now, 10 means you've had some packet loss, but at the same time, it's probably imperceivable. The call would be still considered good. Most people wouldn't notice that. Now, once you start dropping down to a level of 20, they call this an adequate case, meaning, most of the time people are okay with it. It's like moderate, You got a C on the exam. Congrats, you passed, but you didn't do that great. It's an adequate call. Now, if you start dropping below that, you hit 30, which is the next level. They consider that, and this is all standards defined by the ITU, they call this a limiting case, which means this shouldn't happen very often. This should be kind of a poor quality call. People are kind of like, oh, that just sounds funny. I'm losing, it's crackling, or that kind of thing. Once you come down to the next level, which is 45, they call this an exceptional limiting case. It sounds very politically correct. It's kind of like, this is a bad call, but maybe one of these in a blue moon, like once a year, could happen, but, this is typically not a good call. Once you get down to 55, they don't even have a nice little acronym for it. They just say, customers are expected to react strongly, meaning, bad. This level, you can't understand the other person, the call got dropped, This is a horrible call and it's rated horribly between the two. Now, when you come in here and you start typing ICPF and you type in your threshold, this one only lets you go to 30. Now, the standard will let you go up to 55. But Cisco routers say, you know what, right here we're going to draw the line. And if it goes, above 30, above 30, it's rated, lower is better, we're not even going to let you rate it that high. So you might say, I want to say, if the call falls below adequate, which maybe is an ICP-IF rating of 20, I want to deny the call. So at this point, it's already begun sending probes, and it's using just default settings right now, sending probes across the wide area network and testing that connection to make sure it's okay. Now we could type in VZOut monitor probe codec and choose, I just erased my IP address. I could put a codec and then choose what kind of codec I want those probe packets to emulate. You can see they only let you use the two options that Cisco is very good at, G.711 for the United States and another place, meaning outside the United States, and then two forms of G.729, the Annex A, G729A, and normal G729 packets that you can send across. By default, it sends a codec of G.711. So you have, all these thresholds that you can configure, but even if you just set the default settings, it's already testing it and making sure that it doesn't fall below an adequate call level. If it does, it automatically busies out the ports to the PBX to where the PBX can no longer use this connection and will hopefully fail over to the PSTN. The other type of measurement-based CAC is the most useful form of call admission control, in my opinion. It's called PSTN fallback, but it doesn't have to involve the PSTN. It can actually cause dial peers to fall between each other whenever the WAN conditions exceed a certain amount. Here's the idea. As a matter of fact, let's jump back to our router. I'm going to do that show dial peer voice summary. And once again, let's focus on our dial peer 43 and 44. Both of them are for this destination, and both of them are going to different IP addresses. So this one right here with a preference of 1 is a backup for the other. Now what I can do is I can use PSTN fallback to test the WAN connection for this top one right here. And if it ever goes below a certain level of quality. I can have it fail over. Now that level is very flexible with how you want to enable that. Matter of fact, let me show you. I'm going to go under, first off, the dial peer 43 and type in the command call fallback. That enables the feature. As a matter of fact, I'll show you. There's only one command you can type in. This enables this dial peer to fall back to other dial peers if the quality ever drops below a certain amount. Now the quality levels are defined on a global basis. They don't have it on a per dial peer because Cisco figured, you know what, you probably have a certain quality standard you want to define for all of them that you want them to meet. You don't want to have, one quality level really good and then another quality level not so good, because you always want your voice quality good. So globally defining it saves you the trouble of typing all these commands under each dial peer. But the commands all start with call fallback, and you have a whole list of options. Now I'm not going to go through all of them, just the primary ones that you'll use to configure PSTN fallback. The main one that I use is the threshold command, this one right here. It allows you to say how bad is too bad. I'll type in threshold, followed by, and it lets you either type in that ICPIF value, so I can say ICPIF and what quality level I want to meet, or maybe I don't trust that system. Maybe I'm like, you know what, I want to define it myself. I want to go in there and say if the delay of packets are getting above, we'll say, 150 milliseconds. That's, Cisco's one-way standard for voice, right? So if it goes above 150 milliseconds and the loss, maybe the packet loss is getting above, 5%. Let's, once we go above 5% packet loss, then I want to divert the call. So I've defined my own thresholds that I can have for delay and loss. That's the primary two, the big ones that I really want to keep track of. Now I can also type in call fallback, and there's a whole bunch of options. I can do a jitter probe and test the jitter, and if the jitter's above a certain amount, cause it to fail over. I can actually have it go through and just monitor this. It says I can monitor destinations without failing over, and this is awesome because you can use your SNMP monitoring tools like MRTG to monitor the quality of lines. I mean, they sell. All right, I'm going to digress. They sell all kinds of stuff for you to buy. Monitor this, pay $1,000, HP OpenView, monitor this, monitor this. We generate pretty graphs, and I'm telling you, you can do everything free. You just take a little more time than buying the product, right? Linux has just about every free application you could ever want for monitoring a Cisco router. And, okay, maybe you're not a Linux person, you're like me, you're a Windows guy. Well, in that case, they've, just about every Linux tool has been modified to work using Perl with Windows. And if you just take a little time some evening and kind of get the gist of Perl scripting, you can really do just about anything all these tools do for free. Okay, done digressing. That's the idea of this. I can set up monitoring and use my free tools to watch all of these, graph them on a nice pretty web page so I can watch and have hard data that I can refer to watch the quality of my voice lines. But the one we want to type is this one, active. Call fallback active. That one allows it to fail over to alternate dial peers if there is network congestion, meaning if the quality goes outside of what you've specified in your thresholds. Now, like I said, there's a lot of different parameters that you can configure in here, but the primary one for voice over IP is this threshold. That is the most useful one in my opinion because, it's called PSTN fallback because most people don't have a backup WAN connection to fail between. They just use the PSTN. But you can fail between whatever dial peers you want to just by enabling those dial peers by using that call fallback command. These last two mechanisms, the resource-based call admission control, I don't want to get too deep into because this is primarily the focus of the Gateway Gatekeeper course. As the name of the course implies, the gatekeeper is primarily used anytime you want to control a large voice over IP network and have a central point of wide area network bandwidth control. And you're probably wondering what this picture is. Anytime I think of the gatekeeper, I think of a movie I saw a long time ago with David Bowie in it called Labyrinth, and he was the gatekeeper of the labyrinth that this poor little child was trying to get to. Anytime you see David Bowie in a film, looking like this. You know that's some high quality cinematography. You have to go see that one. Right. Resource Reservation Protocol is what RSVP stands for. And this protocol allows you to literally carve out bandwidth from your wide area network connection and reserve it for a voice call that's going across. If you want guaranteed voice quality, this is the only true way to get it. The problem, and the reason RSVP isn't everywhere, is because every single router in the chain has to support it, which means if you're using VPN connections or if you're using any kind of network that's not under your control, well, at that point, RSVP isn't an option. What happens is, and also if you use RSVP wrong, you can kill your wide area network. If this is using a G.711 call, let's say it's going to reserve 80 kilobits per second. It will, before the call goes through, send an RSVP request to every single router along this chain. All routers will carve 80 kilobits per second out of every single wide area network connection in between them. That will be dedicated to that phone during the duration of that call. It cannot be touched by anybody. Literally, your WAN link gets slower for everybody else because 80 kilobits is reserved. This is awesome for flawless quality. However, again, every router along the chain has to support it, and that also runs into iOS versioning issues and so on if all your routers don't support it. Let's go ahead and let me show you a sample RSVP configuration. Oh, and check this out. It is awesome. You see Avbo kicked in and failed. It says, fail, fallback. I've kicked over the fallback mechanism because the probe to 10.1.1.1 failed. That was the IP address I just made up. Codec that it used was G.729, which is Annex A. That's what the R8 is. Oh, actually, that's a big point to bring up. I mentioned that the default codec that it used up here was, let's see if I can find it, was G.711 if you don't change any configuration. I don't have it in the list. But for Avbo, if you're using voice over IP peers, the default codec it uses is G.7. Oh, you know what? Sorry about that. I've been highlighting this, but it's off your screen. There we go. The probe failed. The codec it uses G.729 Annex A. And it shows, the ICPF standard that it was trying to meet was 20, but loss, -1, delay, -1. That's because it could not contact that peer on the other side. So that's a pretty good status message that we're able to see Avbo in action. Now with RSVP, let me do I'll just jump under our one test dial peer we've been using. I'll use dial peer voice 43. And in order to enable our dial peer for RSVP, you just type in REQ QoS. The required quality of service is going to be guaranteed delay, meaning I want to guarantee that bandwidth is there for the quality of service, and that's going to be the request. The acceptable quality of service level will also be guaranteed delay, meaning when this dial peer is used, it will send out a request that I need guaranteed delay, meaning reserve this bandwidth the whole way. That goes to the other router on the other side. And the only way that the call will go through is if it gets that guaranteed delay. That's the acceptable QoS level. Now, from there, that's configuring the dial peer for RSVP. We need to go under the physical interface. We'll say interface serial 0/3/0, which is my WAN connection on this router, and type in the command IP RSVP followed by the bandwidth. And you can see there's a lot of other options you can enable for RSVP. But the bandwidth reservation that you want to configure for this. The first line that you have is the total reservable bandwidth on this router or on this interface. So I can say out of all the bandwidth available on this serial link, 500 kilobits per second is reservable. This is a good one to configure so RSVP doesn't eat your WAN link alive. The second parameter that you configure here is how much bandwidth can be reserved per call. That allows you to say, maybe I don't want certain codecs. I'll put 30 kilobits per second per call and hit enter. And that allows you to reserve that 30 kilobits per call with a maximum of 500 kilobits per second on the interface. At that point, you cannot use G711 on that link because that goes far above 30 kilobits per second. That will now allow this router to reserve the bandwidth for that one dial peer whenever it tries to communicate to the other side. We'd have to do that for every single connection all the way through on our chain that we have to the other side of the link. That's why RSVP is always considered an end-to-end mechanism. All routers have to be able to reserve that bandwidth. So to wrap things up, what we've seen in here, I think it's a phenomenal feature, is call admission control. Testing your lines to make sure that they will work for voice over IP. And if not, they will fail over to other dial peers and other preferences of connections that you might have. So the first thing we did was talk about what it is, what call admission control is all about. That's what I just explained. We talked about the various types of call admission control, trying to find out what mechanism we would like to use, and those types are listed right here. Local, measurement-based, and resource-based call admission control mechanisms. Local being the simplest, looking at the physical DS0 limitations or the maximum connections that you'll type in, or we can use that LiveBo mechanism, the local voice busy out, that allows you to detect if an interface is down and then busy out your voice ports that might connect to a PBX if so. I would, however, like to use the measurement-based ones that does everything that LiveBo does and then some more by using the AVBO mechanism, the advanced voice busy out. That will send probes across the line to test the connection, and if it's either down or doesn't meet a certain quality level, it will busy out those ports. The other type of measurement-based CAC mechanism is PSTN fallback, which I figure to be the most useful, since you can measure any type of connection and then jump down to another dial peer if a certain connection doesn't meet your quality standards. Finally, the resource-based call admission control mechanisms, like the Gatekeeper and RSVP, allow you to guarantee that the bandwidth will be available for the call. Most of that configuration in that application is covered in that Gateway Gatekeeper course. So I hope this has been informative for you, and I'd like to thank you for viewing.